Hey again, everybody. This is our solution to problem 3b, so a continuation of 3. This is from Superquiz 3, and once again, we're given a series. We want to determine whether it converges or diverges. And in this case, the most obvious test for me anyway to want to use is the limit comparison test. So I basically have powers of n, right? Sums of powers of n on the top and the bottom. And all I'm doing is taking a look and seeing what are the highest powers of n that I can find. And I want to compare that sequence that we're given to the sequence that's just the ratio of the highest powers of n. So what I claim is if I take the underlying sequence, which I'm just copying now painstakingly, that this is asymptotically equivalent to the sequence where I take the highest power of n, so here it'd be n cubed, right? I don't even have to worry about the coefficient, over, okay, now on the bottom it's a little tricky, so, okay, certainly it's not the 4, it could be the n. Now I have a square root, except it's not a square root, it's a fourth root, and inside it's an n to the 8th plus 2. Now the plus 2 is going to be irrelevant when n is large, so I really think of this as being a fourth root of n to the 8th. So the fourth root of n to the 8th, that's the same as n squared, and that's definitely going to be bigger than the n. So I'm going to put here an n squared. And of course, n cubed over n is equal just to n. So my claim, right, and we'll have to prove this, but my claim is that this sequence, right, the underlying sequence for our series, is asymptotically equivalent to the sequence n. And because that's true, and because we know that the series for n is going to diverge, then this original series is going to diverge. Okay, so assuming this is true, we know that the series, right, where you just add up n, right, as n goes from 0 to infinity, this diverges. And so by the limit comparison test, the original series, and I don't want to copy it, but I might as well, I've already started, this series must diverge as well. Okay, it's actually equivalent. Okay, so this diverges. Right? Okay, so the only thing I have to do in order to justify then that the series diverges is to justify this claim that this sequence is asymptotically equivalent to n. So to do that, we're going to take the limit as n goes to infinity of the original sequence, so 4n cubed minus n squared plus 7 over 4 plus 6n plus the fourth root of n to the 8th plus 2. And we need to divide it by n. So it's going to be the same thing as multiplying by 1 over n. All right, and if we can show that this is equal to a positive constant, then we win the game. So let's see what happens. Right. So first thing is I actually want to start ripping stuff out of this. So in the numerator, I want to rip out an n cubed. So let's see here. If I factor out an n cubed, I can put it over here on the right. So I'll have 4 minus 1 over n plus 7 over n cubed. Okay, and then I have an n cubed over here. And on the bottom, I would like to pull out an n squared. Why the n squared? Well, the same reason we had it up here. Okay, so I'm going to pull this n to the 8th out of the inside here. Okay, so in fact, let's focus on this a little bit. So fourth root n to the 8th plus 2. I can rewrite this as the fourth root of n to the 8th times 1 plus 2 over n to the 8th. And then I can break up this fourth root as the fourth root of n to the 8th and the fourth root of 1 plus 2 over n to the 8th. And of course, this piece right here is just going to equal n squared. Okay, so that's where I'm getting an n squared. That's how I'm going to get an n squared out of this fourth root part. The other bits are not nearly as challenging. I just pull the n squared directly out. I'll get 4 over n squared plus 6 over n. And then this n squared that comes out will just leave behind this fourth root of 1 plus 2 over n to the 8th power. Okay, and I already had one n outside, so the n squared I pull out will now give me an n cubed. Now these n cubes are going to cancel. The minus 1 over n, okay, that's just going to go to 0. 7 over n cubed, that goes to 0. 4 over n squared goes to 0. 6 over n goes to 0. And now let's see, 2 over n to the 8th goes to 0. And so I'm just left with a fourth root of 1, which is 1. And so in total, I'm getting 4 plus 0 plus 0 over 0 plus 0 plus 1. Okay, again, the n cubes canceled. And so my limit is 4 over 1, which is certainly some positive constant. Okay, and this implies that those two sequences are asymptotically equivalent. Okay, and so now we're justified in using the limit comparison test. Now, some people might be tempted to use the comparison test on this problem, and I'm not saying you can't use it. It's just a little challenging here. You have this minus and this plus in the top, and if you, of course, we know at the end of the day this is supposed to diverge. So if you're trying to show this is bigger than something, well, if you get rid of the minus n squared, you're actually making this even bigger, right? But if you get rid of the plus 7, then you're making this thing smaller. And that's no good, right? Like one of them is making it bigger, one's making it smaller. So that's going to make using the comparison test just a little bit more challenging to do here, right? And I think limit comparison test is much easier conceptually. Like you immediately can just count out, okay, I got 3 n's on top, I have 2 n's on the bottom, so it's really just asymptotically equivalent to n. So the series is going to diverge. Now the fact that the original sequence is asymptotically equivalent to n does suggest another way we could have solved this problem, right? It may not have been obvious right from the beginning, but we have one way of actually proving that a series diverges directly, right? Which is like right from the start, which is the non-vanishing sequence test, which is if I just look at the sequence and as n goes to infinity, this sequence does not converge to 0, then the series is going to have to diverge. So let's quickly see what happens if we take the limit of the sequence without the 1 over n. Well, the only difference between what we see here and what we would get in that case is we wouldn't have this times 1 over n, right? We were using that to show that these two sequences were asymptotically equivalent. So instead of having n cubed over n cubed, we would have n cubed over n squared, right? So this would be n cubed, oops, we want green, n cubed over n squared instead, which would be an n. And so in the end here, we would have 4n over 1, which would go to infinity. All right, so alternatively, we could say take the limit as n goes to infinity of 4n cubed minus n squared plus 7 over 4 plus 6n plus the fourth root of n to the 8th plus 2. And this limit is equal to infinity. Therefore, in particular, it does not converge to 0, right? So by the non-vanishing sequence test, the original series, and I won't copy all that down, diverges. All right, so if you can see that right off the bat, that's even better in this case. But sometimes it's not, it's not so easy to see that till you get to the very end.